Jai Hind everyone. This is Jyoti Sharma, Assistant Professor, Department of Electrical and Electronics Engineering in Ajay Kumar Garg Engineering College, Ghaziabad. So today's topic would be the starting methods of synchronous motor, which is one of the topic in Unit 4, which is electrical machines, under the subject Fundamentals of Electrical Engineering under AKTU, having the code of BEE 101. Okay, coming to the topic, which is the starting methods of synchronous motor. So the very first thing, that why do we require the starting methods for synchronous motor? Is it not self-starting? So truly speaking, a synchronous motor is not self-starting. So first, just briefly going with why it is not self-starting. So a three-phase synchronous motor, it is basically working under the principle of magnetic locking, right? So the synchronous motor is a doubly excited motor. That means we used to give the supply to the stator as well as the rotor. Both are being excited, right? Although with a different supply. Likewise, so if at all I say, this is the stator. The stator used to be the armature in case of synchronous machines, right? So this stator would be fed with a three-phase AC supply, right? Whereas the rotor, which can be a salient pole one or a smooth cylindrical one, say for studying purpose, we generally go with the salient pole. So if it is a salient pole structure having two poles, it is a two-pole synchronous motor, right? So its field is also here. On the rotor, we used to have field. Its field is also excited, not only the stator, but the field is also excited, that too with the DC supply. It is fed with the DC supply. So that's why a three-phase synchronous motor is being called as a doubly excited system. Its stator is also being excited and the rotor is also being excited. So what used to happen, as we give a three-phase AC supply to the stator, obviously there will be a rotating magnetic field being created in the stator. The rotating magnetic field, which is running with the speed of ns, which is given by 120 F by P. This ns is the synchronous speed at which the rotor is rotating. The rotating magnetic field is rotating with the speed of ns, whereas the stator, the rotor, is being fed with a DC supply. Now what will happen? Initially, if at all I say, the stator will adjust itself for the same number of poles as that of rotor. If it is a two-pole rotor, the stator will also form two poles. Say for instance, if the pole created here is north and the pole created here is south, right? And instantly, if it happens that here the south pole is being created and the north pole is being created in the rotor, and the both, as we can see, these are opposite poles coming towards each other. So there will be a strong force of attraction between the two opposite poles and their magnetic axis would be aligned. There will be an alignment with the magnetic axis. Once those magnetic axes are being aligned, the magnetic locking occurs. Once the magnetic locking occurs, now obviously this rotating magnetic field, which is running at a speed of ns, will drag the rotor into synchronism, and now the rotor will also rotate with the same speed as that of ns, right? This is the working principle. That is how generally the synchronous motor has to work. It will be working. But the thing is, if that is so, why we required starting methods? So if at all I say, there has to be a magnetic locking between the stator and rotor poles, but every time this locking will happen, this is not going to be happening every time, right? So if at all this rotor, what we have just drawn, is not exactly in the same position and is being placed like slightly tilted, right? In that case, say if it is in this case, it is placed like this, right? And the poles being created, when we give a DC supply, to it, so here the south pole is being created and here the north pole is being created, right? So now what is happening? Once again, the opposite poles are coming nearby. So there will be a force of attraction. This north pole will attract the south pole towards its side, and similarly the this north pole would be attracted towards this south pole. So there will be ultimately this rotor will feel the torque produced in the clockwise direction, right? But the reason is, once again, this is the rotating magnetic field which is produced in the stator. So, and as the motor, it has to overcome the inertia to move in that particular direction. Till it get overs that inertia, right, the stator poles will get changed, right? It is having a frequency of 50 hertz. So in once again, it is going to change for 50 cycles, right? So it is going to be changing very soon. So at the very instant, this would be now the south pole being created, and here will be having the north pole being created. Here will be having south, and here will be having north. Here we will be having south, and here we will be having north, right? Now these are the common poles. This is also south, this is also south, this is also north, this is also north. So what is going to happen? These are the same poles, these are going to repel each other. So there will be a force of repulsion. With that, now the rotor will try to rotate in anti-clockwise direction, right? As the rotor overcomes this inertia and try to move in the anti-clockwise direction, once again the poles will change, as in the first case, right? This will once again become north, this will once again become south, right? So opposite poles will be near about. So once again it will be in the clockwise direction. So this clockwise, anti-clockwise, to fro, to fro, to fro. So the motor is not able to make a unidirectional torque in one direction, right? And it is not going to have the magnetic locking. Until unless the magnetic locking is not being done, the magnetic axes are not being aligned, this motor is not going to run in any of the direction, right? And for that to happen, we require certain starting methods. So what just it suddenly come to our mind that what should happen if at all, what we should make a change in the circuit, that we should have a magnetic locking, we should have an opposite poles created nearby, so that there is a force of attraction, and now finally the magnetic locking is done. So the very first thing which comes into our mind is by providing certain external torque, right, to the rotor initially, right, by making the rotor to rotate in one particular direction by giving some external torque, right. So depending upon that, we will be discussing certain starting methods of the synchronous motor. So the very first method of starting synchronous motor, that is by using pony motors. Starting methods, the very first method is by using pony motors. What are pony motors? These are small AC motors, right? These are small AC motors which are being coupled with the rotor circuit. Now, if at all I say once again, this is the stator circuit, right? And this would be fed with a 3-phase AC supply. Then we are having the rotor circuit. We are having the shaft as well. And with this shaft, we'll be coupling a small pony motor, right? And this rotor needs to be fed with the DC supply, but we'll make a small change in it, that with this DC supply, we'll be having a switch being connected, which is presently opened, right? So the poles will not be formed until unless this key is being closed, the switch is being closed, right? So once we give a 3-phase AC supply, we know what is going to happen now. So there will be a production of rotating magnetic field, which is rotating at a speed of ns given by 120 F by P. Okay. Now what will happen? The rotor conductors, do we have any poles being created in the rotor? No, because the DC supply is off now. But what we are doing, with the help of this pony motor, which is having its speed almost equals to ns, in fact slightly lesser than ns, right? It is not exactly equal to ns of the synchronous motor, what we want. So it will be having a speed almost equal to ns, will make this rotor to rotate in the same direction and almost with the same speed, right. Now when the rotor is rotating with a speed which is almost equals to ns, will switch on the DC supply, will switch on the switch. The key would be closed. If that is so, the DC supply would be fed. At one instant this will happen, that if at all, here we are having, say, here we are having south pole, this will definitely happen at one instant, that here will be having a north pole. And if it is south here, this will be north here, right. At one instant this will definitely happen, that their magnetic axis will be aligned and there will be a magnetic locking occurring. Once the magnetic locking is being done, now this rotating magnetic field will drag the rotor into synchronism with itself, such that now the rotor will also rotate in the same speed, in the same direction as that of the rotating magnetic field, which is ns. Now the rotor will continuously run at a speed of ns, that is synchronous speed. That is why it is also being called as synchronous motor, because this motor is going to run only with the speed of ns, right. So this is the very first method of starting synchronous motor. The another one is just to finish off with this, now once the motor is now running with the speed of ns, now what about this pony motor? Now we don't require this pony motor right now, right. The starting of the motor has been now done. Now the motor is continuously running at ns. Now we can easily decouple the pony motor, as this is just coupled with the rotor circuit with the coupling, right. We will be decoupling the pony motor. This is now no more required in the circuit, right. So this is the very first method. The another method of starting three-phase synchronous motor is by using DC exciter. It is basically a motor generator set, a DC motor generator set, right. Once again it will be coupled to, as its function is almost same as that of what we just gone with the pony motors. Instead of small AC motors, we will be having a DC motor generator set, right. What will be happening in this case is, once again, this is the stator to which we are feeding a three-phase AC supply, okay. Then we are having the rotor circuit. Now its shaft is being coupled to a DC exciter, right, and the field is being excited with the DC, which is actually coming from the exciter circuit, So what is actually happening in this case is, once we give a three-phase AC supply, this is a DC exciter, it is a motor generator set, right. Initially it is working as a motor which is fed with the generator. It is working with the generator, the voltage, the supply is being fed with the generator. So the motor will give the initial torque what we require. Instead of that, in the previous case we were getting it from the pony motors, now we will be getting it from the DC motor. Now the one thing what is important is, the speed of this DC motor should once again be almost equals to ns or slightly lesser than ns, right. That was the requirement in the earlier case also and now also. So the DC motor what we are considering over here should have its speed almost slightly lesser than ns. Now in this case, once again, the motor, the one we give a three-phase AC supply, there will be a production of rotating magnetic field rotating at a speed of ns. Then initially this switch is opened, right. This DC motor will provide the initial torque. The rotor will also rotate at a speed which is nearly equal to ns. Now the DC generator which is actually taking its initial torque from the motor as well, will give the supply. The switch would be given closed, and now this will be exciting the field circuit, right. Now once it excites the field circuit, the poles would be formed. At one instant this will be happening, that will be having a magnetic locking occurring, will be having an opposite poles being created nearby so that the magnetic locking occurs. Once the magnetic locking is done, then now the rotor will once again be rotating with the same speed as that of ns. Right? So, this is the second method in which we go for a DC exciter. This is a very common method of starting synchronous motor. Now, the third, which is very interesting starting method, third method, the very first one what we discussed was the pony motors, which are small AC motors coupled, right. Similarly, the DC exciter, which is once again coupled to the rotor circuit. Now, are the damper windings. The third method is by using damper winding. Now, what we understand with a damper winding? Now, a damper winding, these are the extra winding, right. If at all I go with once again the stator circuit, which is being fed with 3-phase AC supply. Now, here we do not couple any extra motor, neither AC neither DC, to the rotor. What we do instead is, in the stator circuit, in the rotor circuit as it is, which is having, it is a salient pole construction, right. So, the poles are projected outward, as having a heavy pole shoe, fine. Now, what we used to do was, in these pole shoe, we used to have the poles being, the copper or the aluminium, we used to have aluminium or copper bars inserted in these pole shoes, and these are being, actually these are the bars, right, the copper bars which are running throughout the length, and these are being short circuited with the help of end rings. So, this used to form exactly the same formation as that for a squirrel cage induction motor rotor, right. As we used to have a squirrel cage rotor, it forms the same kind of construction. So, we are having two windings in the system, two field windings. One is the main rotor winding, one is the main rotor winding, right, which is to which will be feeding the DC supply, right. We will be feeding here, we do not require any switch also. So, we will be having the main DC, the main field winding which will be fed with the DC supply, and in addition to the main field winding, will be once again be providing one more winding, which is being called as a damper winding, which is exactly in the same fashion as that of a squirrel cage rotor, having the copper or aluminium bars being inserted in the pole shoes and are being short circuited from both the ends using the end rings, right. Now, if that is so, and we give a 3-phase AC supply, how this is going to work, right. When we give a 3-phase AC supply, obviously there will be a production of rotating magnetic field in the stator, okay. So, this rotating magnetic field will be having a speed of ns, fine. Now, initially, now what we are doing? The DC supply, in fact, initially we will not be providing any DC supply to it, we are having switch in it. We are not going to give any DC supply right now. So, if at all we see like in this case, only the 3-phase AC supply is being given, the rotating magnetic field is there rotating at a speed of ns, and now the rotor circuit is available, right. But the rotor circuit is now short circuited, it is exactly the same as that for a squirrel cage induction motor. So, these rotor conductors will experience flux cut because of the rotating magnetic field, right. So, they will experience flux cut, they will have induced EMF because of the Faraday's law, induced EMF, then the current, as these are short circuited, the current will be flowing in these copper bars in the conductors, and now this is now a current carrying conductor placed in a magnetic field will experience torque. It is the same theory as implied for a 3-phase induction motor, right. So, the rotor will experience a torque in the same direction as that of ns, but will rotate. Will it rotate with the same speed as that of ns? No, it will rotate with a speed nr, right, which is slightly lesser than ns, and we want this, right. So, instead of providing any external mechanism for providing the torque, what we are doing is we are providing an external, an extra winding in the rotor circuit itself, which will be making the circuit to look like a squirrel cage induction motor. It will start like a squirrel cage induction motor, which with that the rotor will rotate at a speed of nr, which is slightly lesser than ns. Now, our purpose is solved. Now, we will give the DC supply, switch on the DC supply, right. Once we give the DC supply, the main winding will come in action, right, the poles would be created. Once the poles are created, obviously at one instant we will be having opposite poles being attracted and will be having being done. Once the magnetic locking is being done, once again the rotating magnetic field will drag the rotor into synchronism, and now the rotor will be rotating at a speed of ns, not nr, right. It will be rotating with a speed of ns. So, this is how we are making it to work with the help of a winding, extra winding, what we are calling it as damper winding. Now, what again now? In case of earlier cases, we can decouple the extra mechanism what we are adding, but in this case, now this is inside, right, we can't decouple it, we can't make it outside, but now this is a squirrel. Now, if you just see, it has started like a squirrel cage induction motor, fine. Now, the relative motion between the rotating magnetic field and the rotor, this becomes 0, because rotating magnetic field is having the speed of ns. Now, the rotor is also rotating at a speed of ns. There is no relative speed. If there is no relative speed between the rotating magnetic field and rotor conductors, the rotor conductors will not be having any flux cut, no induced EMF, no current, no torque, right, by the rotor conductors, by the damper windings, right. So, the damper windings will be there in the circuit without producing any extra torque now, right. So, they will be remaining inside this. The disadvantage of this proper method is actually we are having copper bars or the aluminum bars are being inserted. So, the rotor is heavy also, and it is having rotor copper losses also, the efficiency is also less, the power factor of this kind of motor itself is very lesser. So, that is why it is less being used, right, but this is one of the way by which we can be implementing the starting, or we can start the 3-phase synchronous motor. The last method, that is the fourth method, that is by having a slip ring induction motor. Slip ring induction motor, likewise in the earlier case what we have seen, by using the damper winding we have made a synchronous motor to start like a squirrel cage induction motor, and then it converts itself to a synchronous motor. A 3-phase induction motor, initially it used to, squirrel cage induction motor it used to work like, and then it worked with the synchronous motor. Similarly, in this case we will make certain arrangements with the slip ring induction motor so that later on it works like a synchronous motor. Fine, a 3-phase slip ring induction motor. The rotor circuit, I am only drawing the, say if it is star connected, right. It is star connected. Say this is the shaft what we are having. Now, in the slip ring induction motor, that is the most advantageous thing is we can be having the 3 terminals being taken out. Now, these 3 terminals can be connected with the slip ring and the brush assembly. These are the slip rings, these are the brushes, and now with the brushes we can be having the external resistances being connected, right. That is used to be the conventional way. Now, what we are going to do this time is we are going to have the connections of these being taken out like this, right. Once again we are going to have a dual pole switches being connected. These are the dual pole switches. Here once again we are having the DC supply terminals. DC supply terminals. Fine. So, now we can be seeing initially this is nothing but a slip ring induction motor, right? So the motor will initially work like a 3-phase slip ring induction motor. These rotor conductors will give a 3-phase supply to the stator, rotating magnetic field would be there. Now these rotor conductors will experience flux cut, they will have an induced EMF, then obviously the current and then the torque. The rotor will also rotate, right, with the speed of NR, which is slightly lesser than NS, and this is what we want. But this will be when these switches, what you are seeing, are towards the right hand side, right? These switches are on the right hand side. That means these switches are being closed towards this side. That means only variable resistances are being connected, right? No DC supply is being given to the rotor circuit. External resistances are being connected. So in this case, what is going to happen? It will going to start exactly like the same as that for a slip ring induction motor. So that the rotor rotates with the speed of Ns, which is slightly lesser than Ns. Fine, that is what we want, right? Now the rotor is rotating at certain speed Nr, which is almost equals to Ns. Now what will be doing? Now the switches would be closed towards the left side. That means towards the DC supply. Now these rotor will be supplied with the DC supply, right? So once the DC supply is being given, now the rotor will also have the poles being created. In the stator also we are having the poles. At one instant this will be happening that there will be a magnetic locking, there will be opposite poles being attracted, the magnetic axis would be aligned, the magnetic locking will be done. Once the magnetic locking is done, now the rotor will continuously run at a speed of Ns instead of Nr, right? So this is what we want. These are the 4 usual methods of starting 3-phase synchronous motor. Thank you all for listening so patiently.